Assalamu alaikum class. I hope that all of you are well and safe in your homes inshallah. This is lecture 32 of our course Signals and Systems. This is a different lecture because I have not prepared any slides for it to deliver the lecture from. However, whatever content we'll cover today will be put on slides with lecture 31 so that you can refer to it afterwards. Now this lecture is going to extend our concept of Fourier transform. We have seen that Fourier transform so far. In fact, we have seen that Fourier transform is used to observe the frequency content of an aperiodic or a finite energy signal. We have seen through different examples how to determine Fourier transform for a time domain function. Today we'll start by determining the inverse Fourier transform of a function given x of j omega. We'll also see that the concept of Fourier transform can be extended to include the periodic signals as well, and hence we can say that Fourier transform is a unified approach to determine the frequency content of both an aperiodic and a periodic signal. So first of all, we'll start our lecture with an example. This is example 4.5 of your book, and this example is going to be used to determine the inverse Fourier transform. Suppose for instance we are given x of j omega is equal to 1, 0, omega is less than capital W and omega is greater than capital W, where capital W is the width or W, width for the wave. Now you can also see from the lecture book, in fact on the left hand side of this, that this waveform resembles a pulse in the frequency domain, or this is a band limited function in the frequency domain. So naturally, since we concluded our lecture 31 with the example where we determined the Fourier transform of a time domain pulse, and we saw that it was a sinc function. Today we will see that whether the reverse is also true. So to determine the inverse Laplace transform, inverse Fourier transform, we use the formula xt is 1 by 2 pi integrating from minus infinity to infinity, because the spectrum we expect exists from minus infinity to infinity. And for the inverse transform, we always take a positive exponent multiplied by positive exponential. So this becomes integration between minus omega and minus w and plus w, minus omega t dt. For the inverse transform, since the transform is a function of omega, so we'll integrate it with respect to omega. Now when we integrate this function with respect to omega, since we are integrating the exponential, it remains as such, and it's being divided by the argument of the exponential, which is 1 by jt. We have to keep it in our mind that we are integrating this function with respect to omega, and the limits of integration are minus omega 2 w2 plus w. This is w, capital W width. So this becomes 1 by pi into 1 by t, and again rearranging it like the last lecture by 2j gives us 1 by pi t sine of omega t. Now you observe that it is again sine of omega t divided by t, being a function of t, means that it is again a sinc function. So we remember that the plot of a sinc function is like, now we have to keep it in mind that this is a time domain plot. So it's a time domain plot. This is x of t. We know it's going to be a sinc function. So let's plot the sinc function and find the rest of the values afterwards. So what is the value at t is equal to 0? We differentiate both numerator and denominator and substitute t is equal to 0. So x of 0 is 1 by pi cos of omega cos of omega t, and we'll substitute t is equal to 0. This becomes omega by pi. This is w. I don't know this w and omega keeps on getting mixed for me. This is w, this is w, this is w. Because after I substitute the value of w is equal to omega is equal to w, so it gets w over here. So this value is w over pi. Where are the zero crossings? When the argument omega t is wt is equal to plus minus m pi. So the first crossing is at pi by omega, pi by w, the second is at pi by 2w, and so forth. So now let's label the plot. We know the magnitude at this point is w by pi. This point is pi by w. This point is pi by 2w. This point is minus pi by w. This is minus pi by 2w. Minus 2 pi by w. And so forth. So from this plot we have two observations. The first observation is that when we had a sinc in time, when we had a pulse in time, we had a sinc in frequency. When we have a pulse in frequency, we have a sinc in time. So this brings us the notion of duality, that there is some dual relationship, which means that it is, if the transform of something is A is B, then the transform of B is A, but it might be multiplied or some other simple basic operations could be done with it. So what is it? We'll discuss in our next lecture when we will discuss the property of duality. It is also seen that now the impulse was band limited. The pulse was band limited. This pulse is band limited. So when a function is band limited, it is time unlimited. So if there is a limitation, it can be only in one domain. Either the function will be band limited or the function will be time limited. It does not mean that a function cannot be unlimited in both domains. This is mostly the case. A function is unlimited in time and unlimited in frequency. But if it is limited in one domain, then it must be unlimited in the other domain. So we have seen from this example how to determine the inverse Laplace transform, and we have also observed some relationship between time and frequency. Now we are going to discuss another important concept, which is Fourier transform of a periodic signal. This is article 4.2 of your book. So we are going to see what is the Fourier transform. I don't know why is it not showing 4.2. Let's write here. Fourier transform of a periodic signal. Now, when the concept of Fourier transform was introduced, we proceeded by starting from the Fourier series, and we extended the concept of Fourier series by making the periodic signal an aperiodic one. So somebody might think that Fourier transform is probably used for aperiodic signals only. However, this is not true. Fourier transform is a very basic transform which can be applied to both periodic and aperiodic signals. So let us derive, or let us see, what is the relationship between Fourier transform of a periodic signal and Fourier series of a periodic signal, because both are Fourier analysis methods and both are giving us the frequency spectrum, so there must be existing a relationship between the Fourier transform and Fourier series of the periodic signal. So let's say that we have a signal x of t whose Fourier transform is given through an impulse. So we have any signal, say x1 of t, and its Fourier transform is given by this impulse. Now this is a shifted impulse, and this impulse exists at omega is equal to omega naught. If we want to determine this signal x1 of t, we'll use the inverse transform. The inverse transform's formula was given on the previous, I wouldn't say slide, was given in the previous drawing. Let's say 1 by 2 pi minus infinity to infinity 2 pi. This comes from the formula. Again, since the inverse Fourier transform, for the inverse Fourier transform, x of j omega is a function of omega, so we integrate it with respect to omega. This 1 by 2 comes from the formula, and this is the value of x1 j omega. So again, applying shifting property, this 2 pi and this 2 pi gets cancelled, and once I apply the shifting property, we get omega is equal to omega naught, which is equal to e j omega naught t. In case this was delta, I am sorry, I missed writing delta over here. I just saw I didn't write delta impulse. So I'll pause here for a second. And do you observe the symmetry between time and frequency again? Remember example 2 of lecture 31, where we determined the Fourier transform of a shifted impulse, and we saw that it was white noise. It had a magnitude of 1 and a phase component was there, and you see there's a same relationship is here, but now we have 2 pi magnitude appearing next to impulse. Okay, so we are progressing towards our properties soon, and we'll keep all these things in our mind. Coming back to the numerical, now this is e j omega naught t. Now if we have lots of x1 j omegas, we have lots of functions. We have, say, x2 j omega is equal to 2 pi delta omega minus 2 omega naught, and we have so many other functions. We have x3 of j omega, and we have x of, say, minus 2 j omega. So we have lots of functions, lots of individual Fourier transforms, and if we take a combination of all these, add all these harmonically related Fourier transforms, and we say this is k is equal to minus infinity to infinity 2 pi del of omega minus k omega. This takes a form like this. So what I said that say we have a Fourier transform which is a combination of all these shifted impulses. Also, we say that say it has a magnitude A of k. Now this magnitude A of k will appear as such in the time domain function. So when I take the inverse Fourier transform of this function, I get xt is equal to A of k e j k omega naught t. Interestingly, this is the same expression as that of Fourier series. So if we take the inverse Fourier transform of this term, we get the same time domain function as the time domain function we obtain when we synthesize all the terms of the Fourier series, all the Fourier series coefficients, and combine them to form our original function. So this means that for this function x of t, the Fourier transform is a sampled version because it's being multiplied by this impulse which is occurring at k omega naught. So it is the sampled version of ak coefficients and they are being multiplied by 2 pi as well. So the Fourier transform of periodic signal with Fourier series ak can be interpreted as a train of impulses with weight equal to 2 pi times the k Fourier series coefficients. Let's apply this to an example and see how can we determine the Fourier series, the Fourier transform of a periodic signal given the Fourier series coefficients. So this is example 2 of today's lecture and this is example 4.6 of your book. And let's see if I can go to example 4.6 from the book shown on the left. So now example 4.6 of the book continues from a previous example. We take a time domain function x of t which is a rectangular function. It's a rectangular wave. Excuse my drawing again since I want to draw all this on one page, so all the duration of all these steps or all these pulses would not look the same, but it is the same. It is a rectangular wave with all pulses of same width or positives of the same width as all the negatives. So the Fourier transform of this, the Fourier series of this rectangular wave you have solved comes out to be ak is equal to 2 sine k omega naught t1 by k omega naught t. When you were doing Fourier series, as a practice problem, I gave you a table and I asked you to determine the Fourier series coefficients for all those waves. In that figure, that was lecture 27, you were given a rectangular wave and its Fourier transform. Otherwise, we have done many similar problems when you were doing Fourier series, or simply you could determine the Fourier series yourself if you still don't find that example. Now, this AK is again resembling a sink, is a sink, because this is a function of k, and we see that it has sine k to something and it's being divided by k. So this is eventually going to be a sink, or it's going to look like a sink, or the envelope of the resultant expression is going to be like a sink. So in your book we are given that t is equal to 4t1 and the amplitude is 1. So I'll simplify this expression for ak. I'll substitute values because it's easy if I substitute values at this stage, because omega naught is 2 pi by t into t1 divided by k 2 pi by t into t. This t gets cancelled, so this is 2 by 2 pi k sine k. Now I'm substituting the value of t1, t is equal to 4t1. This is 2 pi by 4t1 into t1, and in the next step this also gets solved and we have 1 by k pi sine pi by 2k, because this t1 and this t1 gets cancelled. Now these are our simplified AK coefficients, but we have to determine the Fourier transform of this rectangular wave. So what we do is, we had a formula that Fourier transform of this wave is equal to x of g omega, which is a sample version of AK. So this becomes equal to, once I substitute all the values, k is equal to minus infinity to infinity 2 pi into 1 by k pi sine pi by 2k into del of omega minus k omega naught. And when I solve it further, I get k is equal to minus infinity to infinity. I'm just cancelling the terms. This pi gets cancelled with pi. This 2 remains sine pi by 2k delta omega minus k omega naught. Now we see that although this Fourier transform is a function of omega, but the omega now only exists at discrete intervals, which is k. We have seen from Fourier series that the transform or the series or the frequency domain expression of Fourier series is a discrete signal, or the frequency spectrum of a continuous periodic signal is a discrete signal. Also, the spectrum of a discrete periodic signal is a discrete spectrum. So for a periodic signal, we get a discrete or a line spectrum. And from Fourier transform, we have seen that for an aperiodic signal, we get a continuous spectrum. So this spectrum is going to be discrete, and it will only exist at integer multiples of k. Before plotting the spectrum, let's determine some of its values. We know it's going to be sink. We have seen it from this expression. So let's determine a few values. So when k is equal to 0, we'll have something of from 0 by 0. So we apply L'Hopital rule again. We differentiate numerator and denominator. We get cos pi by 2 k, and once we substitute the limits, we get pi. Similarly, For k is equal to 1, we get 2 by 2 because it is being divided by k. So it's 2 by 2 sine pi by 2 into 1, which is equal to 2, because sine of pi by 2 is positive 1. When k is equal to 2, we have 2 by 2, should be 2 by 1, sorry. We have 2 by 2 sine pi by 2 into 2, which is equal to 0. For k is equal to 3, we have 2 by 3 sine 3 pi by 2 into 3, which is equal to, sine of 3 pi by 2 is equal to minus 1, so we have minus 2 by 3, and so forth. And since it's a real function, so its magnitude plot is going to be even symmetric, or its general plot will look like it is even symmetry because it has no phase. These zero crossings can also be determined by, as we know, substituting the argument of the sinc function equal to m pi. So the argument of the sinc function for us would be, let me bring you the sinc function. So the sinc function was sine pi by 2 k. What sinc belong to what existed due to this sine function. So we say that pi by 2 k should be equal to m pi plus minus m pi. So k is equal to 2 by pi into m pi, or k is equal to 2m. So the first zero crossing is at, for k is equal to 2 into 1, which is at 2. Second zero crossing is at 2, which is 4, and so forth. So let's, given these values, let's plot this function, and I've taken the liberty of plotting this function over here. Yeah. And where are my values? Let me put my values over here so that we can observe them easily. So I think it's easy. So we can see it now, both of them. So we see that when k is equal to 0, we had a magnitude of pi, which I didn't write, but I'll write it here. The magnitude was pi. For the value of k equal to, it looks like 1, but if you observe here, the frequency is minus 1 omega naught, so this impulse exists at omega naught. So at frequency omega naught, the magnitude is 2. Similarly, when k is equal to 2, this impulse exists at del omega minus 2 omega naught. So at 2 omega naught, we had a value of 0. At k is equal to 3, we have the impulse 3 omega naught, so the value was minus 2 by 3. At 4, the value should be again a 0, and so forth. So the envelope of this transform is that of a sinc function, but the transform is being shown by green lines here. It is this value and this value, this impulse and this value and this value, and so forth, which is also shown by the figure in your book, but your book did not give this value, so I've just given in some extra values for you to see how we get these values. So this brings us to the last example of our lecture. We'll continue with the concept of Fourier transform of periodic signals, and somehow in these two lectures we have covered so many important signals which are not only useful for your course signals and systems, they'll also be useful for your course communication systems. So example 3 is example 4.8 of your book. and we are going to determine the Fourier transform of an impulse train. So the impulse train is such that it is a periodic impulse train. So it exists at first impulse comes at t, the second comes at 2t, third comes at 3t, and so forth. And one comes at 0 to minus 2t, oh sorry, it should be t, minus 2t, and so forth. So this is a periodic impulse train. This periodic impulse train can also be written as x of t is equal to k varies from minus infinity to plus infinity del of t minus kt. So this is another form, this is a mathematical form to describe this impulse train. Now we have to determine the Fourier transform of this impulse train, and we know to determine the Fourier transform of a periodic function, we have to know the Fourier series coefficients of this function. So the Fourier series coefficients for the impulse train can be determined by substituting in the Fourier series formula the values. So this is the formula for Fourier series, and we determine the Fourier coefficients. Whenever there is delta, you should be very happy, because you know you have to apply the shifting property, and the point where this delta or impulse exists is the point where your function gives you a value. So this is 1 by t e to the power minus j k omega naught t, and t is equal to 0. I just do this extra step for you, because if I substitute the direct value, I remember when we used to have lectures in the class, you used to ask me for each to write do each and every step. So I am doing each and every step. This is 1 by t, and we remember that omega naught is equal to 2 pi by t. So x of j omega is, substituting the values simply, 2 pi a k del of omega minus k omega naught. So x of j omega is equal to 2 pi by t, k is equal to minus infinity del omega minus k. What is omega naught? 2 pi by t into, that's it. So this 2 pi comes from the formula, this t comes from the Fourier coefficients, and we have substituted the value for omega naught as 2 pi by t. Now if we plot this function, this also looks like an impulse train, and now this impulse train is occurring at values of integer multiples of 2 pi by t. So if I plot this impulse train is going to look like this waveform, x of j omega. The first one will exist at del omega minus k is 1, 2 pi by t. The first one will exist at 2 pi by t. The second one will exist at 2 into 2 pi by t, which is 4 pi by t, and so forth. What is the magnitude of all these impulses? The magnitude of these impulses is 2 pi by t. So we can summarize the result by saying that an impulse train in the time domain gives us an impulse train in the frequency domain. Also, we can observe that if we increase this time t, so that the impulses in time are further apart or are expanded, because in the frequency domain these impulses are divided by t, so they'll come closer. If this t becomes from 1 second to 2 seconds, so this will go further, but over here this will squeeze. So this also reinforces one concept which we discussed in Fourier series, which was expansion in time is compression in frequency, and vice versa. And again, this brings us to the conclusion that there is a relationship between time and frequency domains. There exists a relationship, and if you see the two, because of this 2 pi in this example and the previous example, that relationship comes something which involves 2 pi as a magnitude. So this concludes today's lecture. For the third lecture of this week and first lecture of next week, I am going to cover the properties of Fourier transform, and since I like having all the properties in one lecture, so I'll try to upload that lecture by Wednesday or Thursday, so that there's a complete lecture, the final lecture for this week and the lecture for next week, and for those of you who are following regularly, they can do those properties. In the presentation for lecture 31, I'll include these examples for lecture 32. I'll also note down the examples and numericals that we have covered so far. I have seen the views on my YouTube page, and not everybody is following the lectures because some lectures have 30, 35 views, and the strength of your classes is a lot. So I advise you that those who are not following, kindly try to follow the lecture in time. Obviously, will be having a little extra time at the end to cover the lectures, but if a group is doing it together, so if you get stuck and if, say for instance, I'm not responding, which is it doesn't happen very often, so you can discuss it with your class fellow as well. Again, I'm available for you on telephone, on email, on WhatsApp, whatever you like. Wishing you all the best. Allah Hafiz.